Get ready for a cosmic journey like no other. India's ISRO is on the brink of an incredible feat, launching a mission to the Sun. With the upcoming Aditya L1 mission, ISRO is about to unlock the secrets of the Sun, our blazing celestial neighbor. Imagine studying solar flares, magnetic fields, and space weather up close. This mission isn't just about gazing at the fiery ball in the sky. It's about understanding its impact on Earth, from satellite communication to power grids. Join us in this video as we break down the science, the technology, and the sheer audacity behind ISRO's mission. We'll explore how they're battling extreme temperatures, radiation, and gravitational forces. Whether you're a space enthusiast or just someone curious about the universe, this solar mission is set to captivate your imagination. Stay tuned as we follow ISRO's journey to touch the Sun and illuminate the mysteries of our solar system. Aditya L1 mission. The first Indian space-based observatory-class solar mission to unlock the mysteries of the Sun. Before we dive headfirst into the exciting world of space missions, let's take a moment to explore the astonishing details of that massive ball of fire that dominates our daytime sky, the Sun. Our Sun is the nearest star and the largest object in the solar system. The estimated age of Sun is about 4.5 billion years. It is a hot, glowing ball of hydrogen and helium gases. The distance to the Sun from the Earth is about 150 million kilometers and is the source of energy for our solar system. Without the solar energy, the life on Earth, as we know, cannot exist. The gravity of the Sun holds all the objects of the solar system together. At the central region of the Sun, known as core, the temperature can reach as high as 15 million degrees Celsius. At this temperature, a process called nuclear fusion takes place in the core which powers the Sun. The visible surface of the Sun, known as photosphere, is relatively cool and has temperature of about 5,500 degrees Celsius. Now let's see why to study Sun. The Sun is the nearest star and therefore can be studied in much more detail as compared to other stars. By studying the Sun, we can learn much more about stars in our Milky Way, as well as about stars in various other galaxies. The Sun is a very dynamic star that extends much beyond what we see. It shows several eruptive phenomena and releases immense amount of energy in the solar system. If such explosive solar phenomena is directed towards the Earth, it could cause various types of disturbances in the near-Earth space environment. Various spacecraft and communication systems are prone to such disturbances, and therefore an early warning of such events is important for taking corrective measures beforehand. In addition to these, if an astronaut is directly exposed to such explosive phenomena, she would be in danger. The various thermal and magnetic phenomena on the Sun are of extreme nature. Thus, the Sun also provides a good natural laboratory to understand those phenomena which cannot be directly studied in the lab. Now let us understand what is space weather. The Sun constantly influences the Earth with radiation, heat, and constant flow of particles and magnetic fields. The constant flow of particles from the Sun is known as solar wind and are mostly composed of high-energy protons. The solar wind fills nearly all the space of the known solar system. Along with the solar wind, the solar magnetic field also fill the solar system. The solar wind, along with other explosive/eruptive solar events like coronal mass ejection, affects the nature of space. During such events, the nature of magnetic field and charged particle environment near to the planet change. In case of the Earth, the interaction of Earth magnetic field with the field carried by coronal mass ejection can trigger a magnetic disturbance near the Earth. Such events can affect the functioning of space assets. Space weather refers to changing environmental conditions in space in the vicinity of Earth and other planets. We use more and more technology in space, as understanding space weather is very important. Also, understanding near-Earth space weather sheds light on the behavior of space weather of other planets. Aditya L1 is the first space-based observatory-class Indian solar mission to study the Sun. The spacecraft is planned to be placed in a halo orbit around the Lagrangian point 1, L1, of the Sun-Earth system, which is about 1.5 million kilometers from the Earth. A satellite placed in the halo orbit around the L1 point has the major advantage of continuously viewing the Sun without any eclipse. This will provide a greater advantage of observing the solar activities continuously. The spacecraft will carry 7 payloads to observe the photosphere, chromosphere, and the outermost layers of the Sun, the corona, using electromagnetic and particle detectors. Using the special vantage point of L1, 4 payloads will directly view the Sun, and the remaining 3 payloads will carry out in situ studies of particles and fields at the Lagrange point L1. The suite of Aditya L1 payloads are expected to provide most crucial information to understand the problems of coronal heating, coronal mass ejection, pre-flare and flare activities, and their characteristics, dynamics of space weather, study of the propagation of particles, fields in the interplanetary medium, etc. Let's see what is Lagrange point. For a two-body gravitational system, the Lagrange points are the positions in space where a small object tends to stay, if put there. These points in space for a two-body system, such as Sun and Earth, can be used by the spacecraft to remain at these positions with reduced fuel consumption. Technically, at Lagrange point, the gravitational pull of the two large bodies equals the necessary centripetal force required for a small object to move with them. For two-body gravitational systems, there are total 5 Lagrange points, denoted as L1, L2, L3, L4, and L5. The Lagrange point L1 lies between Sun-Earth line. The distance of L1 from Earth is approximately 1% of the Earth-Sun distance. Trajectory to L1. The Aditya L1 mission will be launched by ISRO's PSLV-XL rocket from Satish Dhawan Space Center, Sriharikota. Initially, the spacecraft will be placed in a low Earth orbit. Subsequently, the orbit will be made more elliptical, and later the spacecraft will be launched towards the Lagrange point, L1, by using onboard propulsion. As the spacecraft travels towards L1, it will exit the Earth's gravitational sphere of influence. After exit from sphere of influence, the cruise phase will start, and subsequently the spacecraft will be injected into a large halo orbit around L1. The total travel time from launch to L1 would take about 4 months for Aditya L1. Let's see what are the major science objectives of this mission. There are 4 major objectives. They are understanding the coronal heating and solar wind acceleration, understanding initiation of coronal mass ejection flares and near-Earth space weather, to understand coupling and dynamics of the solar atmosphere, to understand solar wind distribution and temperature anisotropy. Now let's see what are the payloads of this mission. The spacecraft carries 7 scientific payloads for systematic study of the Sun. All payloads are indigenously developed in collaboration with various ISRO centers. 7 scientific payloads are Visible Emission Line Coronagraph. This is designed to study solar corona and dynamics of coronal mass ejections. The payload is developed by Indian Institute of Astrophysics, Bengaluru, in close collaboration with ISRO. Solar Ultraviolet Imaging Telescope. This is to image the solar photosphere and chromosphere in near ultraviolet and to measure the solar irradiance variations in near UV. The payload is developed by Inter-University Center for Astronomy and Astrophysics, Pune, in close collaboration with ISRO. Solar Low Energy X-ray Spectrometer and High Energy L1 Orbiting X-ray Spectrometer. These 2 payloads are designed to study the X-ray flares from the Sun over a wide X-ray energy range. Both these payloads are developed at U.R. Rao Satellite Center, Bengaluru. Aditya Solar Wind Particle Experiment and Plasma Analyzer Package for Aditya. These 2 payloads are designed to study the solar wind and energetic ions, as well as their energy distribution. Aspects is developed at Physical Research Laboratory, Ahmedabad. PAPA is developed at Space Physics Laboratory, Vikram Sarabhai Space Center, Thiruvananthapuram. Magnetometer. This payload is capable of measuring interplanetary magnetic fields at the L1 point. The payload is developed at Laboratory for Electro-Optic Systems, Bengaluru. Now let's understand why to study Sun from the space. The Sun emits radiation in nearly all wavelengths along with various energetic particles and magnetic field. The atmosphere of the Earth, as well as its magnetic field, acts as a protective shield, and blocks a number of harmful wavelength radiations, including particles and fields. As various radiations don't reach the surface of the Earth, the instruments from the Earth will not be able to detect such radiation, and solar studies based on these radiations could not be carried out. However, such studies can be carried out by making observations from outside the Earth atmosphere, that is, from space. Similarly, to understand how the solar wind particles and magnetic field from the Sun travel through the interplanetary space, measurements are to be performed from a point which is far away from the influence of the Earth's magnetic field. Is it a complete mission to study the Sun? The obvious answer is a no, which is not only true for Aditya L1, but in general for any space mission. The reason is that due to the limited mass, power, and volume of the spacecraft that carries the scientific payloads in space, only a limited set of instruments with limited capacity can be sent on board the spacecraft. In case of Aditya L1, all the measurements will be made from the Lagrange point L1. As an example, the various phenomena of the Sun are multidirectional, and therefore the directional distribution of energy of explosive phenomena will not be possible to study with L1 alone. Another Lagrange point, known as L5, is a good vantage point for studying the Earth-directed coronal mass ejection events and assessing the space weather. Also, the polar regions of the Sun are not well studied due to technological challenges of achieving spacecraft orbits for such studies. The Sun polar dynamics and magnetic fields are believed to play an important role in deriving the solar cycles. Further, the polarization measurements of solar radiations at different wavelengths are required to understand the various processes occurring in and around the Sun. In conclusion, this mission stands as a remarkable testament to India's unwavering commitment to space exploration and solar studies. The mission's ambitious goal of studying the Sun's outermost layer, the corona, and its impact on space weather holds immense promise for advancing our understanding of the solar dynamics that affect our daily lives. Thank you for joining us on this enlightening journey of discovery. If you feel this video has given you more insights, kindly share it. And by the way, if you haven't subscribed, kindly subscribe to our channel. Thank you.